everyone. As promised, I will start the new series of paper implementation, and the first paper in this series is spectral analysis of lung sounds for classification of asthma and pneumonia wheezing. And here, as you can see, when I search this paper on Google, then we will open its relevant IEEE paper. And today we will basically, in this series, we will see how to implement this paper step by step. And another additional thing that I will be sharing with you guys is its practical deployable GUI, and which you guys can see from here. I will be uploading all the relevant codes, notebooks, and the implemented stuff in this repository. I will also share the link in this YouTube video and the upcoming videos, and I will show you the overall things that we will be going through in this particular paper implementation series. So let me get straight to the deployable part. Yeah, after implementing all the steps and things, you will finally be able to have something like this, a deployable GUI, where you can upload and pre-process your own lung sounds, feature models, and then you can get the results on the dashboard. If you see here, when you upload lung sounds, you will get something like this. Feature extraction step, it will look like this. And after model evaluation, 3 models that we will deploy in this GUI, you will get the results, and the final results give you the prediction whether it's asthma, pneumonia, and wheezing. And whenever you are either using this paper or implementing it, so do cite this paper in your project reports or even if research publications. Okay, now let's talk about the input data. So this is my private data that I uploaded on my GitHub, my Kaggle repository. And if you see this particular data set has 3 classes: asthma, normal, and pneumonia. As when you will read the paper, you will get to know that an asthma has some relevant audios, asthmatic as wheezing audios, normal have normal human lung sounds, and then in pneumonia obviously we have pneumonia wheezing. Now cut short to, this is the first codebook that I will be explaining to you guys in very detail. So by the end of it, you guys not only have the basic knowledge of how to pre-process or clean a lung sound, but also if you cater any kind of biomedical signal. Okay, now before I touch any code part, I want you to imagine something. Imagine you are a doctor with a stethoscope listening to a patient's chest, and then what do you hear? Breathing, but not just breathing. Sometimes you hear normal airflow, sometimes you hear wheezing, as is the case in asthma. Here you can see, if we simply, I'm just trying to make you understand the concept. And sometimes you have crackling in pneumonia. So when these sounds are recorded with a microphone, they are not clean, yet you get silence, background noise, electric hum, maybe even the patient moving the microphone. So our first job before we do any machine learning project or any machine learning implementation is to clean and prepare those signals. And this is what preprocessing means. And we will do this in 3 careful steps here. Now let's start seeing the note. So the first one is the normalization. We make sure loud and soft recordings are treated equally. And in filtration, we will be keeping only the frequency band that contains lung sounds. And in segmentation, we will be chopping the 30-second, 20-second, or whatever long recording you have into smaller meaningful chunks. By the end of this lecture, you will see why preprocessing is not optional. It's the foundation of everything. And here I simply explained the relevant libraries and why do we need them, and some of the global parameters that will stay the same. Okay, so first what we do, whatever, as this is a private dataset, what you can do is that you can either use open source datasets which have relevant pneumonia, asthma, and normal lung sounds and make their folders, and then simply by taking this code you can pass your folder path in this particular spot and you will have your data loaded. And as in this particular case, the sampling rate of the audios is 44.1 kHz, and we are particularly focusing to by filtering when I mentioned the filtering part. So this is the exactly limit that we will be setting, and I will also explain it further. Okay, so let's start by loading one of the audio files. There are .wav files recorded at a sampling frequency of 44.1 kHz. That means every second of lung sound is represented by 44,100 numbers. Think of it like a movie camera. Camera captures 30 frames per second, and an audio recorder captures 44,000 frames per second. That's how detailed the sound is. And by loading the audio, how do you do that? You basically, if you conventionally just want to show or load a single audio file, what you do is that you load a librosa file, basically the librosa library, and then you pass your path and your obviously wherever your recording is. So here you can see that we have the path sampling rate we have fixed, and by giving the pass we are making sure that the sampling rate is equal to what we have fixed, and then we are basically centering the data bias to avoid DC bias before band pass, and then we are applying band pass filter, and then after band pass filter we are applying zero based filtering. And normalization after filtering for later features extraction is optional. Either you can do it here or you can do above this. At this stage, let's talk about a raw signal. And if we see one of the raw signals, which I will show you in this particular paper, if you see raw signals here, the raw signals, they look messy. It's raw, pressure values, sometimes strong, sometimes silent, and we need to fix that. And why do we need that? Because different recordings can be loud or soft. Why? Because maybe the microphone was close to the chest, maybe the patient spoke softly, maybe the environment was noisy, and if we don't normalize, the model might think a loud asthma sound is different from a soft asthma sound. And actually, both are the same disease. So we normalize in two steps. We subtract the mean to center the signal 0 around and divide by the maximum amplitude to scale through -1 and 1. Here, as in this particular formula, you can see. And now if we go to the code, we can see that we have implemented this part here. This min max normalize function is doing that. Now all recordings, no matter how loud or soft, after passing through this min max normalize function, they will be equalized. This ensures that when we later calculate features like spectral energy, it reflects the breathing pattern, not the microphone volume. Simply, this is like adjusting the volume knob on every recording so they all start at the same level. Okay, now the next step is filtration. As I mentioned earlier, that I will make you go through this filtering step. So now, how do we, like, why exactly are we using, why do we need a filter? Imagine you are listening with a stethoscope. Do you care about the sounds of the patient's heart? Not really. In this particular case, you want lung sounds, and what you care about are high-pitched noise from the microphone. No, you want lung sounds here. And after doing detailed literature review, we came to know that lung sounds are concentrated between either 150 or 250 Hz to 2000 Hz. And below 150 Hz is mostly heartbeats, body movements, and electric hum. And above 2000 Hz is microphone hiss and noise. So we built a filter that passes only that range, like tuning your radio to the correct frequency. We use a 10th order Butterworth filter. Why Butterworth? Because it has a flat pass band, meaning it doesn't distort the lung sounds. And here, if you see, this particular code builds a filter and applies this. And obviously the result will be the clean version of the lung sound. And here, if you see the range, there is F low and F high, and we can see that earlier we have defined basically this. We have basically defined the exact part, like 250 to 2000 Hz. That will be the F low and F high. And what does this mean in practice? Wheezes, crackles, bronchial breathing, all preserved heartbeats, microphones, his background noise cone. This is why filtering is essential. Now, the third part is segmentation. And by segmentation means cut the signal into frames. Let's go to the segmentation part. This here is defining the kind of segmentation we will be doing. Now let's understand it. Because lung sounds are non-stationary, that means their properties change with time. A wheeze may last half a second, a crackle may last 1000 milliseconds. If we analyze the whole 30 seconds at once, we miss these fine details. So we divide the signal into 0.25 second frames. Now earlier I mentioned the total signal has 44,000, and if we try to find the 0.25 second frames of that, we will have 11,025 samples with obviously 50% of overlap, which as I mentioned here, so nothing is lost. And this code will give us exactly 239 frames. But wait, many frames are also silence, and silence has no medical meaning. If we feed silence into the classifier, it will confuse the model. So what we do is we calculate frame energy and remove low energy frames by using these two, these short time energy and drop silence frames. After silence removal, only 191 frames remain. That's 80% useful signal and 20% silence removed. This way, the model learns only from meaningful lung sounds. Okay, so this is how I visually call, and you can see that the Butterworth 10th order band pass filter that we designed is only passing the frequency range that we defined earlier. Well, let's see the results. This is the code. Basically, if you only want to pre-process a single lung sound, you apply all the steps, and then when you see it, this is here something that will look like this, and I will giving you the example of this particular one. So let's try to understand it. The fs is the sampling rate of the recording audio, and x raw here is the raw waveform that had 1.32 million samples, which was basically exact 230 seconds of the recording. And x centered, when we subtracted the mean, so the signal oscillates around the 0, and this is the shape of that. Obviously we have normalized the data, so the shape is exactly the same, and xvp is representing the bandpass filtering, and these are the frames. The audio we split into 239 frames, and each is 0.25 second long, and the frames that we kept are 191 after silence removal, and that proves that we kept 80% of them. So instead of what all this preprocessing step proves is that instead of one long messy signal, we now have a short manageable chunks of meaningful sound. Imagine a novel. Instead of reading all 5,000 pages at once, we break it into chapters. And chapters here represent frames, but skip the blank pages, and blank pages are that of silence. Now, if we visualize all three lung sounds, normal, asthma, and pneumonia, and we make it go through all the pre-processing steps that we defined earlier, then we would have something look like this. So all these three, basically this signal is showing the pre-processed signal. Here it is quite visual. If you see it, I will zoom it. Okay, and now here if you see, the normal signal show bursts of airflow. Asthma looks too weak, often irregular, and pneumonia looks flatter with some strong patterns in between. And this already shows that preprocessing is making disease patterns quite visible. And if you see the frequency domain, normal shows strong low frequency components, while asthma shows spread energy more widely. That's why, because wheezing sounds are musical and wheezes create strong frequencies, while pneumonia, as compared to, is weaker with suppressed high energy. So we can clearly see the difference. That is why preprocessing is not just cleaning, it's revealing the medical truth hidden in the signal. So the if we simply summarize this, what we did was we normalized the signals to equalize volume. Then we applied a Butterworth bandpass filter to keep 250 to 2000 Hz. Then we segmented into frames and removed silence. We also visualized time domain and frequency domain signals of preprocessed audios to see that all the preprocessing steps are taken correctly. And this preprocessing pipeline ensures that the raw sound is transformed into a clean, structured input ready for feature extraction in Notebook 2. So in the next lecture, we will calculate spectral features that describe the shape of these lung sounds mathematically. Thank you, and remember, preprocessing may seem boring, but it's the most critical step, and without it, everything else falls apart. And all the links and details are will be shared in the link below. If you like this video, do comment and subscribe. Bye.